And good afternoon, and welcome to this very special presentation of the QEM Heroes webinar series. My name is Christine Wood, and I serve as the Assistant Program Director for the Heroes Fellows Program at QEM. The Heroes Program brings together researchers with experience in the federal government to lend their knowledge, support, and resources to the STEM research and education communities. The resources our heroes provide are always complimentary, and we encourage you to visit the program page on the QEM website to take advantage of all of our heroes have to offer. Today, we're treated to a presentation by a distinguished group of space scientists and policy experts to discuss the history and future of NASA's Artemis program. I'm very proud to introduce our four fellows today. Dr. Quincy Brown has more than 25 years of experience in engineering and technology. Most recently, Quincy served as Director of Space, STEM, and Workforce Policy in the White House National Space Council. Her career includes senior policy roles across two presidencies in the White House Office of Science and Technology Policy, Senior Director for Innovation Research at AnitaB.org, Program Director for STEM Education Research at the American Association for the Advancement of Science, or AAAS, and Computer Science Professor at Bowie State University. Quincy holds a bachelor's degree in electrical engineering and master's and doctoral degrees in computer science. Dr. Aprille Ericsson is a trailblazing aerospace engineer known for many firsts. She is the first Senate-confirmed presidential appointee as Assistant Secretary of Defense for Science and Technology, overseeing a $2 billion enterprise. She was also the first African-American woman to earn an engineering PhD while at NASA Goddard. A Brooklyn native, she earned her BS engineering degree from MIT, as well as an ME and PhD from Howard University. Honored globally, she remains dedicated to advancing spaceflight and innovation. She continues to inspire future generations through education and leadership. Dr. Yulia Goreva is a geochemist by training with a PhD from Caltech, specializing in earth and planetary sciences. She previously served as a scientist at the Smithsonian National Museum of Natural History and as a scientist technologist at NASA's Jet Propulsion Laboratory. And Ken Wright retired from NASA after 40 years of federal service, where he most recently served as a senior policy advisor in the Office of Technology, Policy, and Strategy. Other roles during his career included Director of the NASA Inventions and Contributions Board, Executive Director for the Science and Technology Partnerships Forum, and Agency Lead for Innovation. Ken also served 2 years in the White House Office of Science and Technology Policy, where he led the National Science and Technology Council and lab to market activities. A career highlight was receiving NASA's Outstanding Leadership and Exceptional Service Medals during his distinguished career. And I'll turn the floor over to our presenters. Thank you so much.
Thank you, Christine. I'm going to share my screen. All right, so thank you, Christine, for the great introductions. We will go ahead and get started because I know we're tight on time. We will start with, a little bit of introduction beyond what Christine has read about each of us, our personal connection to the space industry and the Artemis program. We'll share a bit of the background about Artemis, kind of where we've been. We'll get into a lot of detail about the Artemis program itself. This is the kind of where we are, where we're going. And then kind of wrap up with opportunities and partnerships. So really how you can engage and connect with all of what's happening now and what will happen in the future. And then we'll wrap up with Q&A. So hopefully you all are thinking of questions or have questions that you'd love to ask. So again, I'm Quincy. My connection to the program really started more recently. My background is electrical engineering, computer science. I was not necessarily a space person. While I was at the White House, I spent time in OSTP and the National Space Council, focused on developing a whole of government approach to supporting the space workforce. And so the kind of tagline, inspire, prepare, employ, was the response to how we can use space to inspire people to be interested in STEM fields, but then also identify and remove barriers to entering and staying in the space workforce. And really the goal here, there, and here still is to enable anyone to contribute to or benefit from space activities. So here's a picture of the roadmap that we developed, and then what I call my space boots that have been autographed by more than 20 astronauts, including the Artemis II crew. Yulia.
I love those boots. Uh, Hi, everybody. Sorry for my voice. I'm a little bit under the weather, but I will try to speak a little bit more clearly. I am Yulia. As Christine said, I'm a cosmochemist. My route to this webinar was a little non-linear. I'm a geologist by training, geologist geochemist by training. I loved all my life to learn uh, about our planet from rocks, like what they tell us about our planet and how it formed and where they formed and what conditions and so on and so forth. That evolved in, well, can rocks talk to me about other planets? So I started studying meteorites and trying to learn about learning about asteroids and Mars and Moon from the hand samples that are handed uh, by our solar system, that when we can get a sample in the hand and study that. That transitioned me into, well, we need to know where samples are coming from. So I spent about 10 years working on Mars 2020 mission to return the samples from Mars, meticulously collected samples. The samples were collected, and Perseverance is still climbing. And I'm here on this photo with the twin, Perseverance's twin rover and the twin helicopter, which is a Ingenuity helicopter. That did collect fantastic samples on the surface of Mars. Their fate to be returned is yet to be decided, but as a scientist, would be extremely happy to have those samples in the lab. I also served as a deputy principal scientist for Mars sample return. So as you can see, the theme there, I am interested in not just space industry. I'm interested in this connection of science and technology, and talking to scientists in the engineering worlds and engineers in the science world, and of course to general public, to try to explain to general public the essence of science that we want to get out of other than Earth planetary bodies in our solar system. Sorry, it was a bit too long.
I'm Ken Wright. A lot of my roots in terms of Artemis kind of started from my days back at NASA Langley Research Center. And as a research center, we've dealt with a lot of technologies that were going to later be incorporated into actual missions. And as branch head of the Advanced Sensing and Optical Measurement branch, I was fortunate enough to lead a group of folks who actually did a lot of the early testing of the Orion capsule and the wind tunnel, as you can see on the left-hand side there. That's a early Orion vehicle actually that was tested in the tunnel. And our branch actually made a lot of the wind tunnel measurements in terms of the optical measurement systems. We also tested things like the parachutes that make sure that they were opening up at the correct stage at different types of speed regimes. And so we did a lot of optical testing in terms of targets and making sure that the various parachutes at the various speed regimes were operating correctly. And in the optical piece, we all saw those great images coming from the astronauts who were taking the pictures. We had to actually test those different window properties and window materials to make sure they had the optical properties necessary for high quality measurements, as well as high quality, high definition. Although back when I was testing, this was like 20 years ago, nobody even knew about high definition, but we still made those high quality so they could be used for future things like high definition. And then more recently, as in my role at Office of Technology Policy and Strategy, worked close with some of the folks who were actually developing the Artemis Accords, and we'll talk more about those accords as part of the Artemis mission. Next up.
All right, thanks, Ken. So yeah, my roots kind of go back to when I was a little girl. In first grade, I was very fortunate that a parent brought a TV to school and we got to see the Apollo mission. The one that's dated there is Apollo 9, and it was first grade. All of us little kids kind of gathered around a little teeny black and white TV. And I remember trying to calculate how old some of them were and how old or when I would be that old, because I thought astronauts were pretty old. I, at the time, did not know about Katherine Johnson, who many of us know her from the Hidden Figures movie, but she was actually this person, mathematician, who was able to create and calculate through orbital navigation and lunar navigation calculations the Gemini and Apollo missions. And so it was many years later that I kind of stepped back and looked and said, gee, I've kind of arrived because, of course, like most kids, I've had interest in a lot of other things along the way. But I'm an aerospace engineer, 30 plus years at NASA Goddard Space Flight Center. And then my last year, federal service, I was at the Department of Defense, as it was mentioned. And in both roles, you'll see, I'll talk about in a moment, some of the technology that was developed while I was at NASA Goddard Space Flight Center. So I wanted to start off with us talking a little bit about just the history and where we were, and you'll see that the United States was very much interested in the near side of the moon. Those to the left, that picture shows some of the landing sites. I just blew up the Apollo 12 landing site. And why I show you this, you'll see in a moment how the resolution of our mapping capabilities really changed. It was said that, astronauts looked out the window and kind of said, okay, I think we can kill the engines here. And hopefully we would not tip over because we were inside of a crater or an unparalleled surface. And then on the right side, you see actually some of the landings that was done by China later in 2019 and 2024. So most of the landings, of course, happened in the early 60s and 70s for the US. But many people are really concerned from a security perspective, like what is going on the far side of the moon because we can't see it. And so there was really this challenge and push, I think, consciously from the Department of War also to be engaged in how we get to that other side. Next slide, please. And so here you can see this nicely pictured, bright colored map. It actually came from the Lunar Reconnaissance Orbiter, which was launched in 2009. It was the instrument manager on that particular project. And its primary instrument is called LOLA, the Lunar Orbital Laser Altimeter. We use that technique on quite a bit of our other expeditions with Mars and other places. We also use it on Earth with the ISAT mission, where we actually use laser telemetry. When it hits the surface, we're able to measure very distinctly the distances, and then you get high resolution maps by knowing those distances. This map actually has resolution of about 3 to 4 centimeters. And so it's very helpful in us mapping out the moon and where we would find our next launch site. So it's a really enabling technique. That's really important as you think about where we're going with Artemis. Next slide, please. Ken, you're up.
We're going to talk a little bit about the Artemis Accords because Artemis is not just about the US or not just about NASA. This is many nations that are part of the Artemis vision. And back in 2020, the Department of State, along with NASA, actually had 7 other nations establish these Artemis Accords. And these are non-binding. There's not like a true treaty, but these are principles that really are used to help kind of govern some of the civil exploration and use of space. Because as we know, we're talking about more and more companies, more and more countries getting involved. And so what are some of the things that we need to be at least aware of? And so this kind of builds on some of the 1967 Outer Space Treaty concepts as well, such as the peaceful exploration of space, not looking to try to have militaries up there, but being transparent about the actual purpose and the scientific information that'll be gathered. Interoperability, it's a lot of good discussion can be done in terms of how do we make sure that the safety and sustainability of the various space operations is something that allows for emergencies to be covered, as well as other things as well, including make sure we register the space object, preserve heritage, such as Apollo 11 artifacts. A lot of things can come down and blow out the original footprints from humans that landed on the moon if we aren't careful about preserving those types of things. And then space resources in terms of how do we plan for the resource extraction and deconfliction of any activities. And of course, we've all heard about orbital debris. This is something that can build up if you just have things and don't have a plan for actually how you're going to get rid of things once they get into space or on the lunar surface. As we start out with this eight Artemis signatories, now we're up to over, 60-something, 62, I believe it is, that are Artemis Accords. So you can see that the momentum is building for countries signing on to those principles. And I'm going to turn it over to Yulia, who's going to give you some background on the Artemis program.
Yes, so there is space for everyone. The NASA Artemis program will send astronauts an incredibly difficult mission to explore more of the moon for scientific discovery. There are four currently in talks, but of course planned for or planning of Artemis 5. And I'm going to give you a very short overview of what Artemis 1, Artemis 2, 3, and 4 are. Artemis 1 was an uncrewed test flight that launched in November 2020. It sent the Orion spacecraft on a 25-day journey around the moon and back to validate the SLS Space Launching System rocket and Orion capsule before actually putting astronauts into it on board. The mission was largely successful, though engineers noted unexpected heat shield erosion and some other little issues during re-entry and required further investigation. Artemis 2 just wrapped up. You most likely followed it, or hope you followed it. It flew from April 1 to 11, 2026, only a few weeks ago, as the first crewed flight beyond low Earth orbit since Apollo 17 in 72. This is incredible. And of course, as Aprille already mentioned, this is like, it's also a look at the other side of the moon, on the dark side of the moon. It's never been done before, to the extent that was done by this mission. This is incredible achievement. That was a four-person crew on a 10-day flyby mission. At the closest approach, actually, Orion came within about 4,000 miles, just over 4,000 miles of the lunar surface. So it is kind of a new human spaceflight distance record, distance from the Earth. So that's the Artemis 2. The NASA, of course, is now using the data from this flight to prepare for Artemis 3, targeting in 27. Artemis 3 was originally supposed to land astronauts on the moon. The first time since 72, as I mentioned. That plan was scrapped basically in just early this year. Instead, it's now a dress rehearsal in Earth orbit. The Orion capsule will launch, meet up with one or both commercial landers, and we still don't know whether it's going to be SpaceX or Blue Origin, and practice docking. So Apollo 3, think of it as like, Artemis 3, think of it as a Apollo 9. So it's a dress rehearsal for the landing. Or test the plumbing before you commit to the real thing. So why the change was made? The landers just simply not ready. SpaceX has flown Starship 11 times now, but hasn't really made it to orbit. Blue Origin's lander has even less experience for now. So there's a lot of technological development that is yet to go. And both vehicles still need NASA to certify them for humans. On top of that, Orion capsule itself has issues to fix, as we discovered during Artemis 2 flight. And then new spacesuits by Oxymon Space is also still in development. So even the orbit for this mission, for the Artemis 3 is not really defined yet. NASA is weighing low Earth orbit, which is cheaper and simpler, versus high Earth orbit, which is better simulates the condition near the moon. So bottom line, this mission is about providing the pieces that work together before we actually risk sending people to moon. And Artemis 4 is the mission. It's the first time for humans to set foot on moon since Apollo 17. So current plan is 2 astronauts will land at the lunar solar South Pole. And it's targeted landing in 2028. the challenges is actually enormous. For SpaceX Starship, the vehicle needs to refuel in space by connecting with second Starship tanker, something that's never been done before, never been even demonstrated before. So then it has to fly to Moon and land vertically on unprepared surface. So during 2025 testing, multiple Starships were destroyed in the flight. So there are other challenges, of course, hardware challenges on the rocket side. The Space Launching System, we switched to a new untested upper stage still in the talk. It's a Centaur 5, I believe. And the new mobile launcher as well is in the works. And finally, running the mission control across three organizations, NASA, SpaceX, Blue Origin, simultaneously, something that's never attempted at that level. Next slide, please. So, sorry, I talked through all of it on one slide, but this is actually good. So I'll just reiterate the Artemis 1. This illustration shows the path, this intricate path that the Artemis took around the moon. The next slide actually shows much simpler path because it had actually human on board. It just went around the dark side with the farthest most from the Earth. And next slide is, I think it's Aprille. You're muted, I think.
Sorry. Yeah, so I just wanted to point out we're going to be talking about opportunities to work either with NASA or with other companies. And so this just shows some of the technology that was developed as we proceeded to think and move forward for lunar and then Mars missions. Goddard Space Flight Center is in Greenbelt, Maryland, just outside of DC. The Instrument Systems and Technology Division has multiple technologies that are actually flavored quite a bit through that LOLA, the LRO mission, because there were 6 or 7 different instruments on that mission. And so in a combination of different configurations, there were cryogenics or detectors or telescopes. Quantum was not quite being developed at that point because we're talking about 2009. But that we do see that the quantum sensing would be a critical technology for the future. Microwave and radar measurements, of course, also are very much needed. I think Crater was the instrument on board that provided some of that capability on the LRO mission as well. And NASA is always looking to improve upon technology. So you're seeing just a snapshot of capabilities currently. The one thing I will mention that a picture that's somewhat futuristic is that sort of purplish lander that you see that actually is identifying the opportunity to create fuel. We've been able to see ice in the craters and LRO, which actually was able to identify the configuration and composition of that ice in some of these craters. But the idea that ice could be used with the H2O being broken apart for air, as I mentioned previously, and then potentially for fuel composition. And so the cryogenics would be needed for that. I always like to give a little plug to NASA because we've had some historic missions in the Kobe mission, which is our microwave and radar capabilities. We often partner quite a bit with Yulia's old group, JPL. They have a very strong group that does microwave and radar technology as well. Next slide. And this was just giving you some of the idea where we've seen this water location. You can see again on the dark side of the moon. And then the frozen water detection actually was a depiction that was provided to us with one of our partners from University of Hawaii. And you're going to hear more about opportunities for partnership with universities, academia, and industry in just a little bit. Okay. So transitioning, I know that Yulia's talked a bit about, but we just wanted to, we thought this was a really cool picture showing how we're moving forward. Artemis 3 is already, the SLS stage, core stage has already been rolled out. And that was done earlier in April. And so you can see the stacks here in the large machinery as they roll it out. Okay.
Yes, and this is a slide that actually summarizes the current challenges or technological specifically challenges that Artemis 3 is facing. The chart outlines it's a concept a cartoon or concept drawing of the entire mission, and you can see that you have Artemis 3 launch and then docking with Orion in orbit, and then the crew board Orion from Starship to sort of Orion. So this concept is completely new. Technology is new. There were no dry runs yet. The Blue Origin has really limited flight heritage, and crewed lunar test planned only in the late this year. NASA also has not finalized which lander will fly, but still both landers or both concepts still need human rating certification. And Orion heat shield requires further redesign. Vent line malfunction from Artemis II is still unresolved. The space suits are still in the development. And there are other technological gaps that still are being addressed right now for Artemis 3. Even more so for Artemis 4, since I already mentioned that neither SpaceX nor Blue Origin has completed an uncrewed lunar landing, and this is required before crewed attempt. Then that Starship must demonstrate in orbit propellant transfer. That's the two-vehicle docking that I mentioned, never done at a scale. Vertical landing, SLL upper stage also may need switching. And of course, the lunar South Pole, our target, is permanently shadowed terrain. So there are very big thermal swings, very uncharacterized surface. So there are a lot of challenges ahead of Artemis 4. Next one, please. Yeah. And I want to pass to Ken here because challenges actually create opportunities, and I love how this sort of this connection is made. And when we were preparing this presentation, this is just made me happy. Yes, the challenges. It's incredibly challenging. Any kind of space flight, any kind of mission that never been done before is incredibly challenging. It's technologically, logistically, operationally challenging. Yet challenges. This actually what drives us. That's what drives progress. That's what drives major technological advances and drive opportunities. Ken, it's yours.
Thanks, Yulia. And this particular picture just shows, we just are celebrating Artemis 2 and Artemis 3, as shown earlier. Not only has it been shipped, but it's actually arriving at KSC as we speak. So I think this is a fresh picture that just was taken. So we're already moving forward with the next steps. And it just shows how much planning and effort goes into these launches and missions. And so one of the things that we've heard as we're looking at all the future missions in terms of Artemis 3, 4, 5, and beyond is that a lot of the entities, especially commercial entities, are looking to say, what can we do to make these missions less risky so we don't mind putting our effort into it? So one of the things that NASA has been starting to roll out is this Lunar Innovation Park. It's actually provides some infrastructure capability. You see that picture there where it says reusable LLP, that's Lunar Landing Platform. And that allows you to have a much more stable surface for landing. We know we saw several missions recently where they landed and they were cheering and all of a sudden they realized they fell over, right? They tipped over several times. So things like that are infrastructure. If you had a landing pad situation where those missions could come and land more reliably, then we would like to see a lot more commercial partnerships because they would feel there's less risk associated with those missions. So you can see other things there as shelter, because I don't know if we saw when those little meteors were coming down the surface. That's not a good thing when you know those meteor showers coming if you don't have somewhere that's shelter, if humans are there, especially. So those types of things in terms of additionally power, communications, energy, storage, and distribution are key elements of this Lunar Innovation Park that will be developed, and that will provide that infrastructure that will help make that partnering even more effective. But in order to get there, there's a lot of things that we need to do in terms of technology shortfalls. And so NASA's already been creating this shortfalls list. You actually have a link there to the official 2026 civil space shortfalls. There was a mechanism actually put in place to get feedback from the general public in addition to NASA to say, what are the priorities in terms of these shortfalls? And when we talk about shortfall, what is a shortfall? It's actually a technology that's requiring further development to really meet these missions. And a shortfall and a gap are very similar, except the fact that the gap is widely referred to in terms of the current state of the art, the technology are needed and are known, versus shortfalls might not know all the details of what needed, but we know we aren't where we need to be. And then, of course, some people like to say, well, there's a tech pull where your innovation is needed to meet a documented mission need, or a tech push where it's actually innovation needed to meet an anticipated mission need. So these are just some of the terms that NASA uses. And Yulia has already talked about some of the things that were included in those shortfalls list. Next slide, please. But we know that wherever these are shortfalls, these are the things that kind of drive a lot of the opportunities that you'll see in things like Space Act agreements. We had a partnership discussion a few weeks ago that talked about potential partnerships with NASA. Those partnership opportunities are driven by these shortfalls because they say, hey, we need folks who work on this. NASA knows they cannot achieve all these missions and future missions by themselves. They need to have partnerships, whether that's Space Act Agreement or MIRAP actually is associated with the minority serving institutions, a fund just to set aside to help them get more involved in helping meet these shortfalls as well. And April's going to talk a little bit about SBIR and STTR and even larger contracts. So it has various opportunities depending on what your level of engagement is from your particular college or university or individual. And I just wanted we've already talked about MIRAP in the past, not going to redo that, but this is an opportunity that's open until May 22nd, and it focuses on minority serving institutions and really promoting that research and collaboration that will help meet some of the Artemis objectives. And it's got the link there to that particular engagement opportunity. Over to you, Aprille.
Thanks, Ken. So I want to talk just a little bit about small business and innovator research, known as SBIR, and then the Small Business Technology Transfer, or STTR program, as stated by NASA. If you're coming from the military world, they typically call it SBIR Sitter. Same type of program, just different opportunities. And as we suggest, I would suggest as you look at opportunities that are related to the Artemis program, that you look in both of those portfolios because the Department of War and NASA are somewhat engaged in Artemis, so there may be opportunities in the announcements. Notice that the broad area announcement for NASA just was released on April 21st. So that's just a little bit shy of a week. And you only have 1 month to actually propose. So hopefully if you've been anticipating the call for SBIR Sitter, you've been working on it over the last few weeks, hopefully last few months. And this offers an opportunity to apply for funding for innovative new technology. Just highlighting here and not going to go through all of the different listings, but you'll notice that there are some slight differences between the two programs. The major difference is that the SBIR program requires that the principal investigator is more than 50% employed by this small business, and so they're primarily employed by that entity. For STTR, it's required that a nonprofit entity is part of the partnership in the STTR, and it must be at least 40% of the work. So you'll notice that in the work distribution, that the small business is required to be 66% during phase one, and then 50% during phase two. So those would be just the two that I would highlight, and then you can kind of go through. These slides will be available on our QEM resources. Another thing to note is that we've presented in the past on the SIBR programs, and so there is a taped seminar or recorded seminar that you can get additional information about and some suggestions on how to apply.
So here I go. Okay, so as I mentioned at the beginning, right, my focus in the space industry has really been on the people, right, and highlighting and thinking about the education and workforce pathways. And as we've talked about NASA a lot, but we've also talked about private sector companies, SpaceX, Blue Origin have been mentioned, Boeing are part of this. There are a number of private sector entities that are included, right? And they cover not just parts about space exploration, but including like communications, remote sensing, right? The in-space activities is part of it, but launch. There's the spacecraft manufacturing. So you saw the SLS, right, being manufactured in one state, and then it's transported down the river to Florida, and then there's ground equipment. And this includes a number of areas, right? Some of which have been mentioned, and with respect to technology, but also science. And then these translate again to a number of areas on campus. Some of them are in STEM fields, but some of them are not, right? We need a lot of international relations. Talk about Artemis Accords in this Artemis generation and era being really about international cooperation. We need people who have that expertise to be part of this, foreign affairs, business administration. And so there are a lot of opportunities at 2-year and 4-year institutions to really engage with this. I wanted to share a little bit about kind of what some of the occupations are. So we've mentioned a lot of like what the work is and what is done, but these are the top, I think it's 10, maybe 10, 11 there, occupations, right? That's industry-wide, not just at a particular agency, but industry-wide, where the most common is software developer. But then you see a good number of occupations that don't require 4-year degrees. And so here we're talking about electrical, electronic, and electromechanical assemblers, right? Equipment installers and repairers, general operations and operation managers, customer service representatives, technicians, right? Assemblers, fabricators. Again, your engineers are in there, your industrial engineers, but they're also inspectors, right? Testers. Someone's got to, as we mentioned, a lot of things are unknown, right? And so there's a lot of inspecting and testing that's to be done. And I've included a quote here from an article taken while Artemis I was launching. And so the first planned launch was scrubbed, right? There was an error or fault. And this is a kind of a quote from an article that highlights that the engineers were making progress repairing the area, right? But that technicians, right, constructed a tent-like enclosure. And so this really, to me, highlights the fact that the engineers are involved, the technicians are involved. It really does take a very large and diverse team with all sorts of skills and expertise to be part of this industry. And it's really, really important that we, as we think about the parts of this that we see that excite us, that we also know there's a place for all of us in this industry and in space. Here are a few links. You'll be able to click them when you get the slides about space workforce internships. These are mostly for opportunities for students. I think Ken has mentioned a lot on opportunities for faculty and institutions and companies, but these are opportunities for students. The last one, Space Grant Consortium, does include opportunities for students and also faculty, as noted there. And with that, I think this is the end of our prepared remarks. We really appreciate you all joining us. Thank you very much. We've included all of our email addresses. There is a QR code there where you can learn more about other future events that QEM is hosting. You can learn more about, we are 4 of the QEM heroes, but there are 20 some odd more of us. And so you can learn more about us as well as provide feedback on this webinar.
Thank you so much to our presenters for a fascinating talk. I would like to invite participants to ask questions. You can use the Q&A tool, you can use the chat, or you can raise your hand to come off mute.
I will stop sharing the slides.
I'll start off with questions today. Going back to the shortfall conversation, what are some of the particular challenges with multi-party mission control? So this seems like a new horizon for us where Blue Horizon is Blue Origin, SpaceX and NASA all working together. Are there dynamics there across sectors that pose particular challenges?
I can say that we've been doing this, NASA has been doing this for some time. Like when you look at James Webb Space Telescope, there are so many different countries that were part of that partnership that it required quite a bit. People often said, we as engineers often said, made it much more complicated. But it also helped to share the cost and create technology that we could gather from the different partners. There are always those challenges. And that even happens when you go from site to site with the communication connection. It may be on an island, it may be on a continent, but you will have to hand off from time to time those communication capabilities. I don't know if somebody else wants to add to that.
Yeah, no, I think that's right on point, April. One thing I would just add, I think, is that a lot of the missions with the commercial side of things haven't had humans involved yet. And so when they do have humans, like the crew exploration vehicle, when SpaceX, and of course NASA is right there, and they usually come have a control room at the NASA facility, so it's not like you have to have any kind of blank out or anything. But with the other missions, like April said, they have their own controls and monitoring stations and everything else. But it's yet to be a commercial, opportunity to really partner with NASA, say, to getting folks to the moon, where we have several different entities who'll be involved with that. But I have a feeling that that will be done at Mission Control at NASA's facility in Houston, just to kind of have the mission control piece in one location, even if it's some commercial entities involved, because of the human element there. They don't want any chance of any miscommunication or something going down. We've had tried and true systems at JSC that I'm sure will be used for a while in terms of those human missions, regardless of who the partner is. So.
Thank you so much. And we have a raised hand from Dr. Greg Davis. You're free to come off mute, Greg.
Hey, Christine and panelists, thank you so much for this presentation. I was very curious about a technical issue. You said that the Artemis II mission went 4,000 miles from the lunar surface. That just feels far to me with no atmosphere anyway. How do they choose what that altitude is? And why couldn't it be a mile even? What's the trade-off that they're making when they select that altitude? Thanks.
Since attitude control systems was one of my areas, I'll just say that if you notice, they're really using sort of a lunar swing by technique. And so the gravitational pull helps to thrust us back around and we kind of whip around the moon. And so there are definitely some critical optimization areas that you'll look at with like conserving fuel or how much energy we want to acquire. If you swing out too far, then you might just off into space. So there are those types of things that are taken into play. I'm quite sure from an aesthetic point of view, we want to get as close as possible, but we don't want to get too close where we get pulled into the surface of the moon as well. So that those are the physics of the situation. And there may be other factors that, of course, would play a role in that as well.
Yeah, one thing I'll add too is Apollo 13 actually used the same type of swing by mechanism, but it was a lot closer. And I think one of the things that was intentionally done on this mission was to have them further away so they could get a full perspective of the lunar dark side versus when you're up close, you're only going to see a small portion, right? This was the first time they were able to get that full perspective on the dark side. And I think that was an intentional piece where you still get the swing by pull, but you're far enough away so you can get the full perspective on the dark side of the lunar surface.
Thank you.
And we still have plenty of time for questions. If someone would like to raise their hand to come off mute or use the chat. And Dr. Davis again.
I had another technical question I was curious about. You said the South Pole is permanently shadowed, but it also has large temperature swings. How can it have both?
I have
I
to
think it
think.
depends on the, oh, go ahead.
No,
You
go
want to
ahead,
go ahead?
Ken.
It depends on the region because from what I understand, I'm not a geologist like you. She can get more detail, but they have different craters that have some regions that are permanently shadowed because of the depth of those craters, so they never get sun. But then you have some other regions at the top of those craters where you might have some day and nighttime. Of course, the lunar night is like 2 weeks, right? So even if it's gets some sun in that particular portion, it's going to be going dark for an extended period of time. And when it goes dark, it gets really cold. And so surviving that lunar night is one of the key challenges that's still out there for a lot of the equipment because the batteries don't operate as well at those cold temperatures and that type of thing. So depending on the location at the South Pole, whether you're at the top of a crater or at end of the crater, you can have different situations in terms of sunlight and availability and that type of thing. Yulia, over to you. You're muted.
Sorry. At the South Pole specifically, let me back up a little bit. So the Moon has extreme temperature swings for sort of several interconnected reasons, the entire planet. First, the Moon has essentially no atmosphere. So on Earth, atmosphere acts as a thermal blanket, kind of like wraps the heat at night or traps the heat at night and diffuses sunlight during the day. So the changes are moderated because of the atmosphere. So without that buffer, the lunar surface is directly exposed to the sort of full intensity of solar radiation and the full force of cold space. So next one is that the lunar cycle or day-night cycle is about 30 or 29.5 Earth days long. So that means any given spot sort of stays or bakes in a direct sunlight for roughly 2 weeks straight. So then it sits in darkness for another 2 weeks straight. So surfaces heat up tremendously, like really to a big extent during that prolonged exposure. And of course, they radiate heat during the night. So at the South Pole specifically, the situation, let me just get it, if I get it straight, situation gets a little bit more extreme because basically of the terrain, we have a very low angle of a sunlight illuminating the South Pole. Or any pole, actually. It means tall crater rims and mountain ridges cast very long shadows. So it's not like a permanent shadow. It's the angle of the illumination shadow. So these are the permanently shadowed regions, not the entire pole. So where the temperatures can actually plunge to like minus 400 Fahrenheit. So like 40 Kelvin. Meanwhile, nearby elevated regions that are sort of not in the shadow and catch sunlight can be relatively warm. So you can see that the swing of those temperatures is really, really big, or the magnitude of changes in temperatures is really, really big. So you can have spots just a short distance apart from each other with temperature differences of hundreds of degrees.
That's incredible. Thank you.
Thank you. And we have two additional questions in the Q&A from Dr. Aaron Lynch. First, is it typical to move as quickly as they have for Artemis III?
I would say nothing is really fast. It's been planned for many, many years. As all of my colleagues are like, they're like, yes, it takes so long to plan missions. And I always go back to one of the missions I supported, James Webb Space Telescope. It started at the beginning of my career. Mind you, I was there 30 years before it was launched. And so almost my entire career. Missions like this take lots of planning. It's faster than we probably would have expected if you look at other missions, but I think that we've luckily have some things to go on because of our former experience with Gemini and Apollo that could help with the acceleration of it. Once things are sort of practiced and tried and true, and in this case, when we showed the launch vehicle that has now been stacked, I think that we've been able to, we're very secure in that that's a low risk thing to go ahead and move forward with. And so that's why we've already got the preparation going with that particular piece of subsystem.
That's a good point. And I would just add to that that, that's kind of because of the success of Artemis 1 and 2 with those particular pieces. If something had gone wrong at one of those stages, we wouldn't have been moving this fast. But I think that just kind of shows that they're very comfortable with the data that was received so far from those systems during the first two Artemis test flights and able to move forward relatively quickly. So, yeah.
And a second question from Dr. Aaron Lynch, and related question, what is the typical between mission time for assessment and analysis?
Typical. That's an interesting
I
question.
don't think there is a typical.
Even that's what I wanted to say. Every mission is unique. It's first, and everyone has its own challenges and processing times, and yeah.
I will say that for science missions, there actually is a requirement. Like when you propose a mission, you have a requirement. Usually it's within 30, it can be anywhere from 30 to 90 days that you post science data. But the analysis of the actual mission itself is happening real time. Like the minute we start, we're beginning to analyze subsystems and how they perform. So data analytics and those capabilities are really important so that we can get real-time results as the mission is going on.
That's exactly it. I just want to add from science side, on March 2020, that was 30 days where instruments were, or all the instruments were supposed to make acquired data public. So you basically deposited to PDS system, the planetary, the data system. But the processing of data takes a long time, and it can be not only processed, it can be reprocessed. The instruments can be recalibrated, new standards introduced, and just science is kind of evolving process of discovering the truth, not just a set data point. Even when you publish a paper with already acquired, processed, and interpreted data, there will be another paper a few months later that may reevaluate your results. So it is an evolving process of discovering knowledge.
And I'd say that that whole process is something that's prioritized during even during the mission. When there were some anomalies or things in certain subsystems, they're going to devote a lot of resources to making sure they're crunching on those. And other things that seem to go smoothly have a lower priority, might not get processed as quickly because of the fact that they didn't have a problem throughout either the two previous missions. So I think that processing could lag in terms of systems that are relatively well known, and you might not hear much about those for a while. But other areas where there was a weakness or some type of anomaly, then they're definitely going to put a lot of priority resources on making sure we get that data as quickly as possible.
I know that Yulia focused really on the science and the release of that data, but the engineering teams also like to be able to take the data that they've acquired from the performance of, say, the attitude control system and compare it to the simulation. So you begin to create the models and improve upon your models for future missions based on the results that you've seen in these missions. So it's pretty critical, and we do try to publish and provide that data to the public. It's an ongoing process, but there's so many facets of it that help us to improve for the next mission. Oh, and we should remind ourselves too to say that as you think about partnering from an academic side, though that's actually one of the places that I often found that universities could more readily slide into supporting if they had a great computer science or computer engineering program. If they're able to help with the data products and the analysis piece, then it doesn't require a very large laboratory, it just requires very good computing capabilities.
Thank you so much to our presenters today. We are near time. I want to remind everyone to go to the QEM events page, qem.org/events, to see our future programs and webinars and to register for those. You are also welcome to visit the Heroes Project page to learn more about our Heroes Fellows. Thank you so much for your expertise and for a very engaging talk today. We hope to see you again at one of our webinars.